Hi class, for the next part of our video lecture series for the day is complex eigenvalues, right? So the stuff that we're going to do today, or for this video I should say, is exactly the same thing we did for the last two videos. We are going to find eigenvalues, however they are going to have complex values, okay? So what we're going to do is we'll go over a review of the complex number system and how arithmetic and concepts of trig are applied to complex numbers. So we're going to have a complex number review, and then we will get into how to find eigenvalues and eigenvectors and how to diagonalize when we are talking about complex eigenvalues. Okay, so this video is a little long, mostly because of the review that we're going to have for the complex number system. Right. So the set of complex numbers is notated as capital C. Right. So this is a bold-faced C. Whenever you see this, it means that your numbers are complex. Everything we've been doing so far has been in the real number system. Okay. So no imaginary numbers or no complex numbers, which you should know is a mixture of the reals with the complex numbers, right? So, reals and the imaginaries is what makes up the complex numbers. So, let's say that we have a number that is complex. So Z is a part of C, so it's a complex number. Then Z has the form A plus BI, where A and B are real numbers. Okay, so again, this is notation for things that you are already familiar with, right? A complex number has this form. A and B are regular numbers, 2 and 3, right? So A and B are part of the real numbers, but put together in this form, that makes a complex number, right? We call A the real part. RE of Z is the real part of Z, right? RE for real. Okay, should be very easy to remember. So again, if there was no B present, right, if this was gone, I would have, let's say this was 2 plus 3i. If the 3i was gone, I would have just 2. That's the real part. Okay, the part that makes it complex is the BI, the imaginary part. Okay, so we have the real part, which is A, and the imaginary part, which is B. Adding those two parts together forms a single value in the complex number system. Okay, that's how complex numbers work. So let's talk about the modulus. Okay, the modulus comes from the trig form of our complex numbers. Okay, so we're going to talk about graphing these in the complex number system. Basically, when we think about a complex number, we think about it as a vector in polar coordinates. Okay, and remember, a vector has a length, and so looking at the length of this as a vector is called the modulus. Okay, so the length of Z is the square root of its pieces, right? So A squared plus B squared, square rooted, that is going to be the length of Z, or modulus Z. Okay, so very similar to like having an x squared plus y squared gives you r squared, and the square rooting both sides is the length of r. Okay, that's how you should think about this. The argument of Z is the angle that this complex number forms when we look at it in the complex, in polar coordinates. Okay, so the argument of Z is the angle that it creates, right? So let's look at an example. Let's consider a very easy example. Z is 1 plus 2i. Okay, so if I look at this in the complex number system, okay, the real axis is my x-axis. So A is like the x value. B, okay, is the imaginary axis. So 1 plus 2i means I go over 1 and up 2. If you notice, I have a triangle here. Okay, this is a triangle. The length of this hypotenuse is the modulus of Z, right? Or its components being squared and added together and square rooted. Okay, so the length of z is the modulus of this complex number. The argument theta is the angle that's formed here. Okay, it's going from the real axis as I move up to this position that I terminate at to form this vector. That is the angle right here. Okay, so this x value along the real axis is just the cosine of this triangle multiplied by the length. So remember, if it's a radius of 1, it's just cosine theta. Since this has some length that's not 1, I have to multiply my cosine and my sine by the length to get the cosine value of this, right? The length along the real axis. Similarly, the length along the imaginary axis is the modulus times the sine of the angle that it creates from the real axis. Okay, so the real part of z is equal to z cosine theta, right? This is 1, this is 1, this is 1. The real part, okay, the real part, r of z, right, re of z, 1 is the modulus of z times cosine theta. Okay, similar for the imaginary part of z, it is the modulus of z times the sine of the angle that's formed. Okay, so putting this all together for our example, right, z equals a plus bi is the same as the real part of z plus the imaginary part of z times I, right? And I can rewrite this, since the real part of z is z cosine theta and the imaginary part of z is z sine theta, again, times I. Okay, real part of z, imaginary part. Okay, putting this all together, I have this form, and this is the form that we're going to use. For those of you who are in differential equations, this should look somewhat familiar to you, okay, especially over the last week or so, right? So the polar form of z looks like this. Okay, this result that we got out, okay, that is our polar form of z, right? So if I want to write this in polar form, this is how we do it. Again, you should be familiar with this from Calc 1, from Pre-Cal, and from Trig as well. We do go over this stuff, so again, this should be a review. If not, then that's fine, but take yourself some time to familiarize yourself with complex numbers and their expression in polar form. Okay. Complex numbers come in complex conjugates. They come in pairs. Okay, just like radicals come in radical conjugates, right? Complex numbers come in complex conjugates. So if z is a plus bi, its complex conjugate, we call it z bar, and you're just taking the opposite value for your b value, right? So instead of a plus bi, it's a minus bi. The a stays the same, right? It's the imaginary part that changes sign, right? So that's a complex conjugate. Z bar is how we will refer to this from now on, right? So let's do an example. Let's look at our example, actually. If this is my complex number, right, that one we just graphed, then z bar is 1 minus 2i, that's its complex conjugate, and its modulus is 1 squared plus 2 squared. I don't deal with the I is not involved in the modulus, just the a and the b values. So that gives me square root of 5, okay? And the real part here is 1. The imaginary part is just the 2. It's the part that's attached to the I. So we also know that the real part is modulus z cosine of theta. I don't really know what the angle is here, but I do know the modulus because I just found that. So that gives me 1 equals square root of 5 times cosine theta, right? Because the real part is 1, and it's also this thing. So I'm just using this equality. Real part is 1. It's also equal to this. I know the modulus. The only thing I don't know now is the angle. And I can use my inverse trig function to figure this angle out. I could have also used the sine form to do the same thing, or I can even use the tan form. I could have used tan inverse, which we do later on in this video. Okay, So just make sure you guys are familiar with your trig stuff. There's gonna be not a lot of trig, but there, enough to review this complex information. So my inverse angle, my angle is cosine inverse. 1 divided by root 5 is cosine theta, so cosine theta inverse of that is my angle, which is approximately 1.1071 radians. Remember, this will be out in radians, okay? Degree-wise, I think it was something like, I wrote it down, I didn't put it in the video, but it was something like 63 degrees or something like that, okay? Not super important, I just need to be able to work with this value if need be, okay? So, in polar form, right, if I want to write this in polar form, I have my modulus, okay, root 5, times cosine of the angle, right, in radians, plus I times my modulus, I root 5, times sine times my angle, okay? So I have my modulus, I can put this into polar form. You can do all of that just from your complex value. Right, as long as you know a and b, you can find the modulus. Once you find the modulus, you can find your argument, okay? So now let's talk about Euler's formula, right? This is a very important formula that we're going to go over. It's used a lot in the diffie-q course. We're going to get into diffie-q's in this class also, so it's important to understand how this works, okay? So e to the I theta is cosine of theta plus I sine theta. If you notice, that is very, very similar to this polar form that we have here, right? Without the modulus of z, I have my Euler's formula, right? So we're going to relate these two together. So let's say I have e to the z, but what is z? Z is a complex number, a plus bi, right? So e to the a plus bi, we can use our properties of exponential functions. And I can write it as e to the a times e to the b. And if you notice, this e to the bi is in this form, okay? Assuming that theta is this b value times I, right? And now I have e to the a, so I can write it now in this polar form, okay? E to the a times cosine of b, okay? Because the angle portion now is b. Alright, and e to the a is on the outside of that, so I'm really just writing e to the bi. Right? So cosine b plus I sine b. And I can pull out, or I'm sorry, distribute this e to the a, and I get e to the a cosine b plus I e to the a sine b. Right? Now I want us to look at this a little bit in terms of a function, because this is e to a complex number, but what if I had e to a complex number times x, okay? So looking at our example here, e to the 1 plus 2i for my z, e to the 1 is e, cosine of the 2, and then I get the complementary portion here. If I went e to the 1 plus 2i times x, that's just a e1x cosine 2x, because x is now multiplied by both of these terms, okay? Again, my differential students, you'll notice that this looks very, very familiar to some things that we have talked about when we have complex roots to things, okay? So that will come about in the next video that we make for not next week, but the week after. Technically, next week is spring break, so you guys get a week reprieve. We do have some stuff that is going to be due next week, though, but I'm not assigning any work for that week, okay? You do have work that is assigned this week that will be due next week, but nothing due after that, right? So now let's talk about the fundamental theorem of algebra, okay? So the fundamental theorem of algebra has to do with basically roots of polynomials, okay? Polynomials are extremely, extremely important. Every polynomial of degree n can be factored into this form, okay? I can factor any polynomial at all. So I know we get into times where we're saying, oh, this is it's a prime polynomial, is not factorable over the integers. These are not integers, okay? So when we can't factor over the integers or over the real numbers or the rationals, then we factor over the complex plane, right? So here I can take any polynomial and turn it into factors, where all of these things are complex numbers. Remember, a complex number is the overarching number system. So even your real values are a member, they're a subgroup of the complex numbers. Your real numbers are the set of complex numbers such that the imaginary part is 0. So the real number system is a subset, a subgroup actually, okay, actually a subfield of the complex number system, right? So these can be real, integers, irrationals, rationals, they can be anything, right? So this is the set of numbers that contain all types of numbers, right? So all of these things are some element of complex. They don't necessarily have to be like 1 plus 3i. They can be just 1, which is again still a complex number, right? So if any of these things are a 0 to my polynomial, then its complex conjugate is also 0. So now let's think of this. If I have 1 plus 2i is a 0, actually scratch it. Let's say I have 1 plus 0i, so no complex part, no imaginary part is a 0, then its conjugate, its complex conjugate is also 0 because that's 1 minus 0i. Both of those are just 1. So this holds for even real numbers because, again, for real numbers, the imaginary part is 0, right? So zeros come in pairs. Okay, you have the 0 and its complex conjugate. Sometimes those are just the same number if there's no imaginary part, right? I hope that's not too confusing, but we're going to use this to talk about complex eigenvalues. So let's consider this matrix: 1, -1, 2, and 3. If I want to find my characteristic polynomial, I need to find the determinant of lambda I minus this matrix. So these diagonal values are going to change to 1 and -2. This will turn to lambda minus 1 and lambda minus 3. Okay, and remember, finding the determinant for a 2 by 2 is very, very easy. We have these two minus the product of this two. So lambda minus 1, lambda minus 3, plus 2, right? Because minus a minus 2 from multiplying these things, right? So fairly simple. Multiply this out and add 2. So lambda squared minus 4 lambda plus 3 plus 2, right? And so we have lambda squared minus 4 lambda plus 5, right? So setting this equal to 0 will give us our eigenvalues. Okay, this is non-factorable. Okay, I can't factor this. It's not, there's no way for me to have 1 and 5 add to -4 but multiply to a positive 5. Right, I need two of the same signs and that's not going to work. So when I plug this into the quadratic formula, negative b, so positive 4, 4 squared minus 4ac over 2a. So this is going to be 4 over 2 is a 2, plus or minus 1/2 times the square root of, what is this? 16 minus 20 is a -4. So 2 plus or minus 2i over 2, or just 2 plus or minus I, right? Now, this gives me my two eigenvalues, okay? But since they come as a pair, I only need one, okay? So from the way that complex numbers work, I only need to grab one of these, okay? Your book tells you to grab the one that is 2 minus I or a minus b. I know that we all don't like negative numbers, so I will show you how to do this with the positive value. Okay, so again, everything I'm going to do here is going to be slightly different from the book. This is the method that I was taught. I find that it is a much easier method to use. However, you might run into hiccups when you try to look at your ask for homework help on the WebAssign, or if you go into your textbook for help. Some of the stuff is going to be slightly different. Okay, so I'm going to suggest that you revert to this video, and for the write-up that I'm going to provide for this video, that will be a better source. Again, you know, I don't like saying my method is better than any other method or what have you, but this does keep things simpler, right? It keeps, just like this keeps this in the form of a polynomial. If we use the method the book uses, yes, this will be positive, and I'm sorry, this would still be negative, and this would be positive, and we would have 1 minus lambda, 3 minus lambda, and so all of this will be in the opposite direction, and we'll end up having to pull out a negative, and it just gets very confusing. It doesn't get it's easy to go through, but it's more problems than it's worth. It's much easier to keep it like this in the form of a polynomial, because that's what you guys are used to. You guys have been doing this for at least, you know, 6 or 7 years by now, you know, since middle school, doing algebra in this way, talking about polynomials in this fashion, right? So it's much easier to keep things like this. Also, keeping the 2 plus I form instead of the 2 minus I form will just keep things simpler. We don't have to worry about negative numbers so much. We don't have to, it keeps things simple. Okay, so I hope that, you know, it's not too confusing for you for when you do need extra help and you go to your textbook or what have you. But again, send me an email if you really have questions. I'm more than happy to answer anything that you have. I can help you on your homework. I will not write solutions for your homework problems, but I will definitely help you walk through them. Okay, so long story short, we always choose the positive form. Okay, always. Everything I'm going to show you is with the positive form of our complex eigenvalues, right? So these are our complex eigenvalues. We're just going to choose one, okay? And we'll choose the positive one. So lambda 1 is 2 plus I. So that gives me this system, okay? So again, if we go back, I'm plugging it into this. So 2 plus I into here gives me 2 plus I minus 1. So that's 2 minus 1, which is 1 plus the I, okay? 1 plus I. And then I do that for this eigenvalue, I'm sorry, for this lambda as well, and this is the form that I get out, okay? So again, I'm setting this equal to 0, and I want to solve it. So before I tell you to plug it into your calculator, and that's fine, your calculator will do your reduced row echelon form and solve this for you. Some calculators will for this, the fancy ones, but most of the time they give you out really ugly numbers that is more confusing than it is easy to deal with. So the best option to keep from making mistakes is to just go through this by hand. Again, most of the time these complex ones are going to be just given from 2x2 matrices. They're kind of difficult in and of themselves, so to do this for the 3x3s can be very difficult. Not to say you're not going to have them for 3x3s, but for 2x2s, just doing them by hand. Same for 3x3s, but it's much easier to do this by hand than it is to use your calculator. Okay. So here what I want to do is I want to make this first term 1. So instead of dividing everything by complex number, I'm just going to swap these rows. Okay. And so I get this result out, right? So now I would like to make this entry 1. Okay. So there's a couple ways to do that. The easiest way, I'm just going to introduce fractions. Okay. So I'm going to divide everything by -2. Right. And now I have 1 1/2 minus 1/2 I, 1 plus I, and 1. Right. So I was going to write this out in the video, but I'm going to implore you to do some scratch work on the side for this next one, just to verify that it's true. Okay. I need to get rid of this entry. So R2 is going to become R2 minus this value times R1. So notice that this negative sign will distribute here. This goes away. That's easy. Okay. I designed this so that goes away, it's this one that you need to check. Okay, you need to make sure that what you get here is correct. This is the math that's going to have to happen. So you're going to get 1 minus this value times this thing. Okay, so I would say to take -1 minus I in parentheses and multiply it times this, and then subtract that value from 1. Actually, what you end up getting here when you do this is you're going to get 1, right? It's actually going to go to 0. Okay, so you actually should reduce down to this form. Again, check it. Okay, I didn't have room or take the time to write this, but you definitely you have the result here. Just do it really quickly, just to make sure you are familiar with your arithmetic for complex numbers. Okay, remember when you multiply I times I, you get I squared. I squared is -1. Okay, so that's going to change the signs in a couple of places, but it's really just like multiplying two binomials together, right? So go ahead and maybe pause this video and just double check that value for yourself to make sure you're okay with the arithmetic of the complex number system. Okay, so what this implies then is that x1 is the opposite value of this times x2, because that's our free variable. So then that allows us to make our vector, right? Our x1 eigenvector. So x1 is, if x2 is 1, then this is going to be what I get for x1. Okay, so I have this for x1. Now generally what we do here is this is the only eigenvector I need. I'll show you what the second eigenvector looks like, but this is the only one I'm going to use for all the things I need to do for this, right? For my diagonalization, for everything. Okay, this is the only one that I use. I don't use both eigenvectors. This is the only one that I'm going to use. I separate this into its two parts. I have its real part and its imaginary part. There's no imaginary part for the bottom number, so it's -1/2, 1. That's the real part of this vector, and my imaginary part is I times the imaginary part. Okay, these are the two pieces to this one vector I use as column vectors for my matrix P. Right? I'll show you how to find x2. So let's say we did not use this. Let's say we use the 2 minus I. Well, remember, complex values are conjugates. That works for vectors as well. Okay, the complex conjugate of a vector is x2 bar, right? So these things are related. They come in pairs. So even the eigenvalues are conjugates and the eigenvectors are conjugates as well. So x2 would be this exact same thing, but with the imaginary part being negative, right? We do not use this for P. Your book does. Your book uses, they would have done this whole thing to find this eigenvector, but again, we're using the positive form. We're not using the negative form. We weren't using the conjugate here. We're using the positive. So we don't use this at all. This is only here to show you that if you need x1 and x2, that you're just taking the conjugate of whatever vector it is you found. So that's why we only need one, because they're paired together. Okay. Now for P, again, I'm only using this x1 vector. I don't have to do this whole thing again here, right? I'm only going to use this, right? So to diagonalize A, we only use the x1 vector that comes with the A plus B I form. Okay. So our diagonalization of A is A equals PB, P inverse. Here B is a little different because I have complex values. Okay. It is not like in the last video where it was PD, P inverse. Right. It works the same way, but it's not the same. So here P is made from the real part of the eigenvector we found and the imaginary part of the eigenvector we found. So these two vectors form my matrix for P, and that will be they're linearly independent from each other, and I'm able to find P inverse from this matrix. Okay, so my B, okay, this B matrix, right, that would normally be the diagonal matrix, is made from A, B, negative B, A. here, the A and the B values are coming from my eigenvalue. In this case, 2 plus I. So here, this will be 2 and 2, 1 and negative 1 on this diagonal. Okay? So the B matrix is made up of the elements from my eigenvalue that we have. All right? Now, obviously, it's not a diagonal matrix. Okay? But that's okay. This has a very specific form that we're going to get into in just a second. Okay. This matrix can be factored into a product that is called dilation matrix, that is diagonal, with the modulus of the eigenvalue, right? The modulus, right? So square root of 2 squared plus 1 squared, right? Not I squared, but 1 squared, right? Times what we call the rotation matrix. Okay, so if you remember when we got into linear transformations and we're talking about the vectors that you have from a linear transformation, how it transforms your space into something that's skewed in some way. We looked at at the unit square, and we transformed that into some squared, skewed sort of R2 axis system, right? So we're talking about how to skew something one direction, how to flip it over an axis, either X or Y, or how to take our thing and rotate it, right? This is very, very, very common in physics and engineering. You will use this matrix all the time. It is very, very important matrix, okay? The rotation matrix. Here I'm using the sort of opposite of the rotation matrix because we're using the positive form. The more standard form is to have A, negative B, and positive B, and the rotation matrix as cosine, negative sine, positive sine, cosine. But since we swapped everything and we're using the positive form of the complex number, we have to adjust our formulas in this way. Okay, so that's the difference between my method and your book method, is that we adjusted this formula to coincide with the complex number that we're using. Okay, so again, this rotation matrix, I can't overstress this. It is used a lot, okay, because sometimes the way that you're looking at a system makes a lot more sense if you rotate it by, let's say, 45 degrees or so, so that you can work in it in a standard R2 or R3 system. Okay, so this is very, very, very common matrix to be used, right? So this dilation and rotation matrix, super, super important. And let's talk about this, okay? So the modulus of B is the dilation that is caused by looking at that matrix A. Okay, let's go back a lot real quick. This matrix that we have, this is my matrix A, right? If this is a linear transformation, right, then what it does to all the vectors in my system is this actually skews them, it dilates them, and multiplies them by a scalar up or down, right? It shrinks them or expands them, and it also rotates them. If you look at that 3 blue, 1 brown, they talk about how a transformation takes all of your vectors that look like this maybe, and they skew them and they transform them into looking like something else. So when we're talking about transformations, we were talking about how it skews the axis system into something else. Well, just think about what R2, standard R2 looks like when you turn it into something that's like up and down, and then maybe this way, diagonal, right? I took it from the 90-degree system and I rotated it like 45 degrees or some degree. That's what this transformation does, is it rotates your system and it skews it to either grow or to shrink to some value. So for our regular dp inverse, we can't really talk about what the skew and the rotation is, but when we have the imaginary system, we can talk about what the skew is and what the rotation is. We can in the regular system, and that's what the eigenvalues and the eigenvectors do, right? Here, this serves the same purpose, but we can talk about them separately, okay? So the modulus of lambda is the dilation, right, or the the scaling factor for a vector that's in our system, and theta is the rotation caused by A as a linear transformation in the counterclockwise direction, right? So this way. Just like our regular trig functions, how we move this way along our polar coordinate system, our trig coordinate system, the unit circle, all that stuff is counterclockwise direction. Okay. So this matrix B is called the rotation dilation matrix of A, because this single matrix, if you decide to factor it out, will tell you the dilation and it will tell you the rotation. Okay, so I can now factor B into a product of two matrices as well. So I'm already factoring A into 3 matrices. B can be factored into 2 more. So I can really factor A into 4 matrices. Okay, so P, the dilation matrix, rotation matrix, and P inverse, which is what we're going to get into. Okay, so for our example, 1, -1, 2, 3, we have these 2 eigenvalues. Remember, we're only using the positive form. Okay, if you follow your book, you would use the negative form, but I think it's easier just to use this. My x1 looks like this. Okay, the complex conjugate is x2, which we're not going to need, right? But your homework might ask you for the 2 eigenvectors, so that's what you would use. My P matrix is made up of the column vectors of the real part of x1 and the imaginary part of x1. B comes from the A and B values of lambda, the one that I'm using. Okay, so A is 2, B is 1, because there's only one I, so positive form, negative form there. Okay, and P inverse is just this matrix inverted, right? It's a 2 by 2, so it's really easy to invert this by hand. It's probably faster to do it by hand than it is to plug it into your calculator, honestly, right? Because the determinant is 0 minus 1/2, so that means it's 2, and then you swap these pieces around and you multiply by 2. Okay, so real easy. So if I want to write this as PB P inverse, I have all my pieces, so this times that. Okay. Check this. Always check to make sure you get your initial result out. Okay, so that's the factorization, or diagonalization, I should say, of our matrix A. The dilation of A, I can find right away once I find my lambda. It's easy to do, right? So A squared plus B squared square rooted, or root 5. Okay, and the rotation of A is theta, so I can use my eigenvalue to find theta, like we did before in the beginning of this video, where I gave you in a complex number and I said, hey, this is the argument of that complex number. We can do that. Last time I used the cosine value, right? I used the 2 equals cosine of theta. Here, the general standard is really to use tan inverse. So again, if this is cosine and this is sine, it's just tan inverse of this over that. That's, to me, I think the easiest thing to do. You don't have to find the argument in that case. You just need to put basically B over A. So sine theta over cosine is tan inverse of the imaginary part over the real part, right? Imaginary part over the real part, or 1 over 2. That's easier than saying finding the modulus, which we do have already, and then saying that 2 is equal to the modulus of cosine theta, and then doing some algebra there. I can just put B over A thrown in tan inverse, right? So it's up to you. There's lots of ways. You know how trig works. There's lots and lots of identities and equivalent methods of doing things. So whatever is more familiar with you. But this is pretty much the standard. I showed you the cosine before, just so that you guys have a multitude of ways in the video for doing the same thing, right? So if I throw this in my calculator, I get about 4636 radians. Okay. which is nice, but what the hell is this, right? I don't know what this is. I don't know what degrees it is. I can figure out what degrees it is, but it's not very useful to me. It's an approximation, right? So not to talk bad on all you engineers and physicists in here, but I know you like to approximate things. In math, we need things exact, okay? So this will give me an approximate value. I'll tell you what, later on in this video, I'll talk about what we would have gotten if we used this instead of what we're about to use, right? But we can find this thing exactly, okay? So we can now use this, if we wanted to plug into that rotation matrix. Backwards a little bit, okay? I know the modulus of lambda, and I know that this is the rotation matrix, so I can plug these things in to find out what the rotation matrix looks like, right? But it'll be very, very sloppy because of this radian approximation, right? So an easier thing to do, okay, besides doing this math, is to use linear algebra to find the rotation matrix exactly, right, with exact values once we know the dilation, right? So I just take this relationship I have. I know B is the dilation matrix times the rotation matrix. I know what my dilation is, okay, is root 5. I know how to move things from one side of an equation to the other when I'm working with matrices. So if I want to get this alone, on the left side, I need to multiply by this matrix inverse, okay? So that will make this I, which gets this alone, and this on the left side looks like this, okay? And this is a very, very easy matrix to invert. Again, it's probably faster to do it by hand than it is to plug into your calculator. Remember, it is the diagonal minus this diagonal, so basically 5. So it's 1 over 5 times all of this. You swap these ones, which is the same thing. So this is just root 5 over 5 as an inverse, okay? I also know what B is, okay? B is my A and my B from my eigenvalue. So this as an inverse times my B matrix will give me out my rotation matrix exactly, right? Not in an approximate form, but in an exact form, okay? So when I multiply those together, this is my rotation matrix in an exact form, right? So I just do a little bit of matrix algebra to get this exactly, okay? You can verify this on your own. You can plug into your calculator and get your values out if you need to, but that's fine, right? So if I really needed to figure out what my argument is, I would just set one of these two things equal to each other. Cosine theta equals to this thing, maybe, and do cosine inverse. If you notice, it's the exact same thing that we would have had before. Or I can use the sine, right? Okay. So I can set this up and solve for theta by using cosine inverse of this value. But now what I'm allowed to do is I can factor A further than just A PBP inverse by factoring B as well. Okay. So I have my P matrix. Okay. This is the real part of the eigenvector. The imaginary part of the eigenvector. My B can be split into the dilation matrix times the rotation matrix, and P inverse is just the inverse of this matrix. Okay, so now I factored it into 4 matrices where I have B, I have P, and I have P inverse, right? And again, you always want to check, if I multiply all these out, I have my matrix A. So again, this is from the eigenvectors, the real part and the imaginary part of the eigenvector that we use for A. This is the dilation of our matrix A. This is the rotation matrix of my matrix A. And this is P inverse from here of my matrix A. You multiply all this back, and we got our matrix, okay? Now, your classwork for this video is to do what we just did for this matrix A, okay? So you're going to turn this into PBP inverse, where B is also factored into its dilation rotation matrices, where all the entries in the matrix are given exactly. Okay, so what does that mean? Factor A into a product of 4 matrices of this form, no decimals, right? So your B should also be factored. You should not have any decimal values. So I did use, just for fun or just to check, I used this value, and I made my, I plugged in for cosine of this, sine of 0.4636, negative sine 0.4636. I plugged into here just to see for fun what I would get. And when I plug that into here, instead of having the exact values, I had those decimal forms. I got something like 0.99999, negative 0.99999, 1.9999999, 2.9999, right? So I mean, you can kind of guess where you should be, but you're gonna have round off error, right? If you use approximate values, you're not gonna get the right values. Okay, and that's because we got whole numbers, right? So let's say I gave fractions, then these things are gonna be way off as well, right? So again, just use exact values, write that up, put it into a PDF and upload it. It's going to be due by midnight tonight because I would be giving this to you in class. So this video is about 45 minutes. The last video was, I think, about 20 minutes, half hour, something like that. That's about an hour long of video, plus these 2 classworks I would expect you to take. This is your first time doing it. I'm honestly, I expect it to be about 45 minutes. So that's pretty much our 3 hours. We're a little short. I didn't write up the material necessary for the next part of the content. So I'm going to save that for when we come back from our spring break. Plus, there's a lot of information in these 2 videos, so I don't want to overwhelm you guys. So if you have any questions, then again, feel free to contact me or leave a message in the discussion portion at the top of the Canvas page where it says questions and requests.